Well, thank you very much, and thank you for the invitation and for the opportunity to visit Vilnius and Lithuania for the very first time. The talk that I've brought to share is called Skip the Design Patterns, Architecting with Nouns and Verbs. Again, my name is Brandon Rhodes. So, as a background, a decade ago, I noticed blogs starting to appear that each translated the old design patterns into Python. They were from this old book from the 1990s, Design Patterns, the Elements of Reusable, Object-Oriented Software, by four people whose names no one remembers, and so they're known as the Gang of Four in the industry for having written this famous book. But I was annoyed. It didn't look like these blog posts were written by people who actually used Python, but were using this more as an excuse to make a blog post. The blogs, for example, all translated the singleton design pattern into Python without ever once mentioning that you shouldn't use it. That made me a little annoyed, so I engaged in some annoyance-driven writing. I wrote a little website of my own where I went through the patterns, not just showing how to translate them into Python, but giving some opinion of whether you ever should, giving other options if there were more Pythonic ways to solve a problem. I also did some annoyance-driven talking at some conferences, all the way from a 2012 talk on Python design patterns, all the way up to a recent talk, the classic design patterns. Where are they now? Where in a single talk, I actually got through every single pattern from the old book, rating whether it was useless or useful, and in what contexts you might still use it in Python or another modern language. But all of that left a big unanswered question. If we don't write Python using the old design patterns, what approach are we following instead? This talk is an attempt to give an answer to that. I've been paying attention in the last few months to the shape of my own projects and to the shape of Python projects I really admire, to try to get a sense of, well, what are we doing instead? So, to start with just a very quick summary, and then all these terms will be defined in the course of the talk, I think modern Python code is built from two kinds of object. Verbs, stateless, idempotent functions. One, again, don't worry, I define the terms later in the talk. And second, don't worry, I know there is another pronunciation for idempotent, but this is another accepted pronunciation and I like it better. Verbs are stateless idempotent functions. Nouns are stateful, mutable data. And from what I can tell, we tend to build applications out of combinations of the two rather than mixtures of the two. Verbs we can stack and compose, but as we'll see, the methods of nouns should usually be shallow. So the rest of the talk will be an argument for this architecture and an explanation of this architecture that I'm trying to draw. I think Python programmers learn by progressing through three stages. Procedural coding, followed by experiments in abstraction, followed maybe by the crowning achievement of encapsulation. Procedural is where all your code is in main, or all your code is at the top level of your py file, or where you're using a Jupyter notebook, where the default is generally to be defining all of your names and doing all of your work at the top level of indentation. And let me say immediately, you can have a successful career without ever moving beyond that. There are people who are the heroes in their office because they've written a 50-line py file. Everything happens at the top level. It reads in two CSV files with pandas, merges them, and writes them to output, and saves someone 3 days of work every month because that used to be done by hand in Excel. If your job is automating things, you can have a happy career at the procedural level and never move on. If you do move on, you tend next to learn about functions, about abstraction, about giving names to chunks of operation that you want to reuse or perform multiple times. And then finally, you might do encapsulation, which I'll begin by saying is writing classes, but as we'll see later in the talk, it's a little more complicated than that. But here at the beginning, you can think of this as all code in main versus splitting it into functions versus starting to write some classes. Because it really isn't functions and classes, I'm going to introduce these terms in order to describe the architecture. The procedural programmer is starting out using nouns and verbs. When you're ready for abstraction, you start to invent new verbs. When you reach encapsulation, you're taking the risk of inventing new nouns. You progress thus from that which is easy to that which is hard as you progress from novice to being more expert. And right here at the beginning of the talk, I can go ahead and reveal one of the problems of object-oriented programming. It starts you here. In object-oriented programming, the new programmer starts with attempts to do encapsulation, and it all goes downhill from there. Let's now write some sample code to illustrate the first two levels, procedural thinking and abstraction. Okay, but first, a necessary note on naming, specifically the issue of singular versus plural. In the old days, the singular was my default. I would have a timestamp or the time, or in science code, you can just call the time T, usually without any ambiguity. And it was the plural back then that was special. I would name it a time array, or list, or sequence, or simply the plural times if I had a list or array of times. But then I started using NumPy, where the plural is the default. You tend to write code like this: Pythagoras of x and y, square x, you square y, take the square root. By the way, in science code, if you want to square something, just multiply it by itself. It's apparently faster and more precise than calling the general purpose power function with 2.0 as the second argument. In code like this, x and y, multiplying them together, is x a float or in an array? In NumPy, you can't tell. You might sometimes call this with simple floats, but the code doesn't change at all if you need to call it with whole arrays of numbers to be multiplied together and square rooted. And so NumPy started getting me used to this idea of x being the whole array of x that I want to process. NumPy gave me the habit of singular names for whole sequences. See also relational databases where your table isn't named users, but user even though it holds more than one of them. Well, so if this is the plural, x, then what is the singular? Well, it depends. Sometimes I call it an x item, or an x member, or an x element, a single number from what might be an array. But most often, I pull from the mathematics notation I remember from college, where if you have a sequence, you often designate its individual elements by a subscript. We often use underscores when designating a subscript, and so I might just say underscore I, exactly like the science notation for a generic member of a sequence. So I might say time sub I, subscript I, temperature I, humidity I, naming items in larger arrays with several values. Except if it's just one letter, if I call time T, I cannot bear to call it T underscore I. That is too much underscore. That is 33% underscore in a single symbol, and I can't bear it. So I tend to just call it TI. remembering to myself that that means time item. So in the code that follows, with apologies to those of you who don't use NumPy a lot, my loops are going to look like for TI, for time item, in my list of times. Another warning. I've practiced this talk several times, and I will call Python lists arrays every time because I've been doing too much NumPy. All right, those are my notes on terminology. Hopefully that will help you follow along. All right, the goal here was to use Plotly, a new modern plotting library, to plot the temperature and humidity recorded on a Raspberry Pi. I've purchased and I live in now a historic home in the United States, and I'm planning to restore the old drafty windows over the next few years to make them more airtight. Everyone claims this saves your heating bill, but I wondered, does it really? So I got a little Raspberry Pi that I'd had forever in a drawer from some long ago conference. I found on Adafruit that I could order little dongles that would have little temperature and humidity sensors attached, and I set up a little home server that every minute records the temperature and humidity, because it wouldn't do to restore all my windows and then in 2 years compare my heating bill. Energy prices go up and down, and some winters are harsher than others. Day-by-day data that I can compare to the weather statistics will let me really see how much this affects an old home's heating bill. So I wrote a simple little program in which I actually loaded the data from a file, but I wanted to draw a picture here so that you can see that T, again, I'm not using NumPy today, T is just a plain old list of date times. And then I have a little dictionary data. Temperature and humidity are just lists of floats. That is the right format. A list of date times and a list of floats can directly be passed to the Plotly go.scatter routine, which draws a nice jaggedy line. I looked at it and I was unhappy. I can see several spots there where, when I had the Raspberry Pi unplugged or was moving or updating it, there's missing data, and so there's long little plateaus or jumps, diagonals in the data where I actually don't know what the temperature was, but the plotting library is helpfully trying to connect those 2 points. And so instead of having those misleading straight lines, I wanted to draw the plot where it just left gaps, where it didn't in fact have any data about the temperature and humidity over several minutes or several hours. How will I do that? Well, here's how the data structures look again. List of date times, and let's imagine a list of data. In a few places, the time jumps by several hours from one element to the next instead of 1 minute. So if I have the time array and I'm able to find the spots where the time suddenly jumps ahead, this is what I'll want to do in order to draw the plot I just showed you. I'll want to make 3 go.scatter calls if there are, as in this example, 2 breaks in the time series. I'll want to get the time and the data up to the first break and draw, then the time and the data between the 2 breaks and draw, and then finally draw the rest of the data as a last pair of lines. That will give me the plot that I want. How will this look in code? Well, let's first try it with only one data series. So I've simplified this down. We're only thinking about the temperature at first. What am I going to do to tear T and the data array into little pieces that correspond to each other? Well, I thought about it in a second, and I thought, let's put that in some other code. Let's do that somewhere else. Let's imagine that I've written a routine split. It takes a time array, a data array, and gives me back multiple pairs of arrays, X and Y, for each contiguous bit of times for each segment in the data series. Then I would run through the loop. I would call go.scatter 3 times, and I would get my diagram with gaps. So now I know what split looks like. I've come up with a little API for it, and it was time for me to start writing split. I said def split, time and data. All right, often I kind of write code from the inside out. I often kind of, when I start, like only one thing is clear to me. Like only one bit of the code is clear at first. So I just write that first and then fill in around it. The only thing I can see clearly at first is that I'm going to loop over the times t. And if the current time item minus the previous item is more than a minute, then I'm going to have to put together an x and a y of the data I've seen so far. And immediately I had to stop coding because of a distraction. Look at what this is doing every single time through the loop. It is getting the integer 1, passing it as a keyword argument to a time delta, building a time delta, using it for a comparison, and throwing it away, and building an entire new one the next time through the loop. Everybody says, don't prematurely optimize your code. But the problem is, if it's inefficient, I'm distracted. And it's hard to think about the code until I fixed it. So I prematurely optimize. So, micro pattern number 1. What's a micro pattern? These are the little habits that I have when writing code that are really what guide me during the working day, not those big old design patterns from the old days. Here's a little pattern I often pull out. Extract a constant. Pull it up to the module level, build that time delta once, and I can use it as many times as I want without further expense. And I can now focus on my code. All right, next, where does tprev come from? That's not defined yet, and I know the answer because I've done this before. Micro pattern number 2. Many times before I've written loops where I have to save the previous element so that I can use it, compare to it the next time through. I know just down at the bottom to put tprev equals ti, so that as the for loop then overwrites and reassigns ti at the top, I'm remembering the previous one and can do my subtraction. I have done this many times, so I didn't wait for the name error. Tprev isn't defined. I know I've got to do something about tprev the first time through the loop, because the comparison happens at the top of the loop, but the first assignment of it doesn't happen till the bottom. Oh, I'm an experienced developer. I am the chess player that sees a move ahead. Oh, it's fun once you get a little good at this. Sentinel value. Do you think that's what I'm about to pull out? No. That is an anti-pattern. When I was younger, I might have tried this. Tprev equal none. And then what do you have to do? Every single time through the loop, you have to say, well, if tprev is not none, and then do the subtraction, because of course the subtraction will explode if you try it with a none. That is awful. It requires an extra is not none test merely to make the first time through the loop different. And the type of tprev becomes like date time or none, which is it's just a distraction and horrible. So micro pattern number 3 that I'm actually going to pull out here, that I've used time and time again, is safe initial value. If I set in this case tprev equal to the first time, then I'm safe. The first subtraction will come up with a distant difference of 0 seconds or minutes and won't trigger the if statement. So I much prefer that to trying to check for none. All right, let's now build the 2 lists that I need to hand back, x and y. They need to start as empty lists. Each time through the loop, x gets a time and y gets a data item. And finally, yield our results so that it can be used up in the loop in main. Inside of the if statement, if I discover that I've come to a break in the time series, I yield up the x and y I've built so far and reset them back to being empty lists for the next segment of coherent times. And then, I know what you're thinking. Did I miss something? I know that grouping needs 2 yields. When I was younger, I would often forget the yield at the bottom, and the last x and y I'd accumulated would just get thrown out, and that data would go missing. But I know that I need to put 2 yields, one in the middle every time I find that I'm between groups, and then one at the end to deliver the final 2 groups back to main. I'm done, I said. Look at all of the little micro patterns I know that save me from trouble, and immediately got name error. DI is not defined. So I guess I don't always see ahead. DI isn't defined because in my for loop, I'm only grabbing the item out of the time array. All right, so I need to throw zip around both of those sequences so that I not only have available the current time item I'm looking at, but also the data item so that I can use them both for constructing those lists. This time it worked, and so I was able to produce a plot of, remember, right now we're only looking at a single data series. All right, only one more goal, get the other one plotted. I headed back to main and now put back the code for humidity, but this time also called split on it and also looped to produce multiple segments rather than a single one. And yeah, it worked. The plot came up. It looked fine. It was correct. But something seemed wrong. So I read the code over again. Segments equals split, 4, segments equals split, and then I saw it. It's doing duplicate work. It's going through the work of finding all the gaps in T twice. The first time I call split, it loops over all several thousand times in the array, looking for the splits and finding them. Then I do all of that work over again the second time I call split. And if there's a little micro pattern I use in my code, it's avoid duplicate work. Projects go much better if early on I recognize and remove duplicate work. So can I expand split, which I just wrote, from splitting one list to splitting many, so I can pass in as many data lists as I want? All right, I got split back onto my screen. And I didn't actually write any code. I simply looked and said, oh no. But here I'll sort of show you what went through my head. I thought about the fact that split would now take not one data list, but several, which means that Y, which was so simple before, now would have to be as many lists as there were data lists passed in. I would now have to have zip not only loop over a single time array, but like multiple data arrays. I would need to yield those up. I would need to reset those. And when it got to the part where I had to append, I would have to have a loop inside of my loop to do all of the appends to the multiple data arrays. No. I just thought about what this would look like and what it would be like to try to get everything correct. And I said, nope. That is the technical term. Nope, I am not going to write that code, because I could see that the complexity of this code is outrunning the complexity of my problem. That's a sense that it takes a long time to develop, but it can be very easy to write code that's way more complicated than the problem you're trying to solve. I had a feeling that was happening here. I mean, conceptually. I want to break a few lists into pieces. This shouldn't be that hard. I heard Raymond Hettinger's voice speaking from a distant talk and saying, there must be a better way. So, thinking of Raymond Hettinger reminded me of a micro pattern I think I learned from him. Do one thing at a time. Don't try to do 2 or 3 steps at once in your code. Try to do one thing and do it well and get it finished and accomplished in some data structure that then feeds the next step. And this code both tries to find the gaps in the time series and split both lists at those gaps. It's trying to do 2 operations at once rather than just one. So I had an idea. What if I have a pure little call just called gaps, whose only job is to find the index of each gap in the time series, then a separate routine split that would split a list at those indices, and I could use it over and over again, having only found the gaps once and gone to that expense. All right, I thought, let's try writing gaps. Split becomes gaps, which only needs the time because it's not touching the data now. The zip goes away because I only have one array to loop over, not 2. All I have to yield up is the index of the locations I find. I don't need to do any other work, which means that the X and Y goes away, the other X and Y goes away, the append calls go away. And I wind up with just a simple little loop discovering where the times are discontinuous. Oh, I was a lot happier. So I tried running it and got a name error because I is not defined. Oh, because in the previous version of this split, I never was looking at the index I was at. I was just looking right at the data. I now need to toss an enumerate around the list now so that I'll know where I'm at and can yield that up. All right, this version worked. Let's return to main to think about now how split is going to work. All right, so I started roughing out what would happen in main. I have some ellipses here because I'm not sure. I'm getting these indexes back from gaps. I'm going to do something to t to make it an x, and to the two data arrays to make it a y, and this started to look really familiar. And it suddenly struck me, split already has a name, y'all. It already has a name in Python. It's called slicing. Oh, and suddenly it was clear. My for loop is just going to need to come up with an I and a j. Oh, and it's just slicing to ask for that slice of time, that slice of temperature, and that slice of humidity. Oh, that's going to be really simple, isn't it? That means that I now need to update my for loop so that I get, going back one, gaps should really not just return I, but should return both ends of the segments. It should return both the beginning and end of each segment for the convenience of slicing. And then let's rename it to segment since it's no longer giving a single index of a gap, but it's giving the start and end of each segment of my arrays. The lesson here, again, do one thing at a time by entangling gap finding with list building. In my original version of split, I wound up re-implementing a Python built-in. And I've been using Python for a long time, and yet there I was re-implementing slicing using like 1,000 append calls. This is a lot easier than I thought the problem was, and I'd hidden it from myself. Now, we just need to tweak gaps to turn it into segments, so here we go. Gaps gets renamed to segments. Instead of yielding I, the end of each one, as it's called here, I need to yield both the start and the place where I've found a break in the series of times. And start is 0 the first time through, because the first segment will begin at the beginning of the list. And then each subsequent segment starts right where the previous one left off. Done. And I got my graph with gaps in it, while only scanning t once to find the gaps. Now a single call to my little segments routine lets me split as many time and data arrays as I want while doing no additional search or no additional extra work. All right, so, and this is real code that I wrote a few months ago. We're now finished writing example code. That's enough for us to go on. I want us to now step back and ask, what levels from those levels that I named earlier was I operating at as I did this? Well, first, obviously, I was doing a lot of work at the procedural level, simply using nouns and verbs that other people had provided for me as part of the Python language. What do I mean, nouns and verbs? Nouns. Date time was already there. Lists and dictionaries are already provided by the language. And then also some verbs. I used enumerate, I used zip, and all of these were available for me without my having to implement them. The procedural coder gets to use nouns and verbs without having to design them. They get to benefit from other people's work on design in order to solve problems quickly. The procedural coder uses small micro patterns as they learn how to iterate, learn how to compare, learn how to do math or work with strings. They learn small micro patterns to arrange familiar lines of code to solve a new problem in a new project. But I also operated at a second level. invent new verbs, the level of abstraction, because I wrote a subroutine of my own. It went through a few different versions as it went from being split to being gaps to being segments, but I was defining a verb. What decisions do we face when doing abstraction? Because I didn't really explain myself to keep the example going along. Let's kind of back up and look at 3 habits that I was following as I designed that subroutine. Why did I even introduce a subroutine segments? That's a good first question. Why didn't I loop over the list of date times right here in main? I know what you're thinking. Brandon, you couldn't. It wouldn't fit on the slide. But I legit made it a subroutine in the original code, even when I didn't know yet that it would go on a slide. It seemed a natural subroutine to me because of something I probably heard back in my days in school. Don't mix levels of abstraction, is the way they put it in class. I/O calling go.scatter just feels like a different level of detail than the little details of iterating over a list. It would have felt odd to me to put the little details of iteration in the same place that I'm making these big outward calls to the rest of the world, like go.scatter. And so that was a first motivation, and in this case, the main motivation for my deciding to write a subroutine. But you might ask, if I'm going to write a subroutine, why hide the for loop? Granted that I want my I/O on a different level than my little array operations, why not keep the little array operations up in main and hide all that I/O stuff down in the subroutine? Well, this leads to habit number 2 that I was following. I try to keep I/O near the top rather than burying it. What happens if we bury I/O? What happens if you, subroutines, make things simpler? A will call B, will call C, will finally down at the bottom, I will call go.scatter. What happens when we bury the I/O very deep in our call graph? The I/O gets hidden, yes. We don't see it when we're reading A or B, but it doesn't get decoupled. What do I mean by that? Tightly coupled means, or tightly coupled happens when you can't call A without it calling B, without that calling C, which calls this big I/O routine, go.scatter. You know the symptom. You try writing a test of the code inside of A, and so it saves a Plotly PNG image to disk for you. It's because of subroutines that have significant side effects that you will see people doing a mock.patch of go.scatter to try to turn that off so they can test A or B, or maybe mock.patching C to turn it off so they can test the code of A and B. That's the symptom of coupling. If you're interested in lots of different ways to break pieces of code apart so they're not coupled, there's an online book called Cosmic Python that has a lot of modern design approaches to keeping your code innocent of the details of your particular database or data store or web service. And if you're interested in that, I can highly recommend it. My approach, where possible, is to keep I/O calls up near the top. There was this old concept of, if you're storing data in a tree, of not wanting it to get too deep on one side or the other and rebalancing the tree to try to keep it shallow. I try to do that with my subroutines. Where I can, I try to have them stop, finish, and return some data to main so that main can take the next step instead of every consequence always being a new subroutine. Some people call this the clean architecture or hexagonal architecture. It goes by different names by different consultants. But it's a pattern that I use almost instinctually now. It's a habit of mine. But not always with I/O. Shallow call graphs have benefits even where there isn't a call that has side effects. Habit number 3, shallow call graphs tend to make for code that is testable and reusable. Subroutines, which are kept close, where they're directly invoked by main or invoked by something that main called, are thereby kept under control. Imagine that I built a deep call graph, that instead of main calling gaps or segments and then main calling slicing, imagine that I instead had dealt with the complexity of split by giving it a subroutine that went and found the segments. Then my boss runs in with a new requirement. Oh, we need to let the user now specify at runtime how big a gap segments will detect. The users are annoyed. They have so many little gaps. They want at least a half hour before there's the result of a visible gap in their data. Let's make that configurable. Well, that now means that segments needs an extra piece of information. It now needs to know the interval. It's not always going to be 1 minute that triggers that test. Well, in a deep call graph, we have two options. One is you can pass interval all the way down the call graph so that it reaches the subroutine. Or the other thing we do is you just store interval in a global. You might have seen both of these before if you've been doing a lot of development. We either add to the higher level call split this interval thing that split doesn't really care about, but it needs it to pass it further down. And if this keeps going, split can wind up with a lot of arguments it doesn't care about just so they can be passed further down. Or we just do an end run around the entire, American football analogy there. We don't do an end run. We dodge the problem by having main, when it learns from a config file or command line option what this interval is, it goes and just makes it a global in a module, maybe the one segments lives in. And then segments can just use that global without any of the intermediate routines knowing where the interval went or came from. That is known in the industry as scary action at a distance, and it creates all kinds of surprises when you're debugging code later. It gets around one problem, but is known for causing other problems in certain projects. But either way, main can only give the interval to segments through some kind of level of indirection if the call graph is deep. And that is a cost, either way you do it. But if I can keep the call graph shallow, as I did in this case, main calls segments and gets a result back, and then can call slice itself, the whole problem winds up being avoided, thanks to a shallower call graph. When the requirement arrives, main just passes interval because main itself is making the call to segments, so it can provide as much information as segments wants. Those are the kinds of habits, the kinds of ideas, the kinds of instincts I'm following when I do abstraction, when I create subroutines. They're not like a pattern. They're not like a cookie cutter. They're more like the pirate code. They're more like guidelines. I don't mix levels. I try to decouple from my I/O. I try to go for shallow call graphs. And all those are things that help me write somewhat healthier code as I'm going along and beginning to break out my first subroutines. Through that code example, then, we've now seen, I hope, a bit of an example of what I meant when I said the procedural coder is using nouns and verbs, dictionaries, lists, and they're getting to enjoy data structures they didn't have to invent or specify or design. And a bit of what I mean by abstraction, this decision to move chunks of code into subroutines, into other functions. All right, what do I mean then when I talk about encapsulation, the invention of new nouns? When have we embarked upon encapsulation? For the way I'm using the word in this talk, it is when we attach new behavior to data. It happens when, for the first time, we stop writing subroutines over here on the left side of this diagram and try adding some of our own code over on the data side of our application. Now, warning, merely typing class doesn't mean that you're doing this, doesn't mean that you're doing encapsulation. This small bit of example code is based on Python's logging module. Let's take a look at it. A class filter. It takes a string pattern and saves it away. And then each time it's called with a log message, it returns a verdict, true or false, depending on whether the pattern string appears in the message. Is this, in the way that I've defined the word, a noun? Is this a data structure with behavior attached? No. This is a pure verb. And to convince you, I'm now going to need to be more specific with what I mean by noun and verb. So let me now get quite technical and start defining those terms that I mentioned at the beginning of the talk. For the purposes of this talk, a verb is a stateless, idempotent function. Call, filter.call here, is a stateless, idempotent function. Stateless because it doesn't store the messages, it doesn't update anything on self to remember how many messages have been passed. It's not a data structure that's keeping messages. Each message is passed in, true or false is returned, and it doesn't store it. It's idempotent because you can pass a message 100 times and it will return the same answer 100 times. From one message to the next, it is making independent decisions that will always come out the same given the same message. This class implements a verb. It's just really a function that's customized at runtime. The only difference between this and a plain old function that you define with def is that it's configurable, is that you get to pass the pattern ahead of time and then get a callable that's just a single argument function that does the test. Why is logging designed this way? Why use a class? Well, because logging often doesn't learn its filters and handlers until runtime. Very often, your logging is set up by command line options, by settings in a config.ini file, so you have no idea until runtime whether you'll be doing filtering or what strings you'll be filtering on if you are doing it. A configured logger in the Python standard library keeps any filter objects that it's been given and handler objects it's been configured with in plain Python lists, a simple data structure inside of an object. The rule is that when given a log message, it passes it by all the filters. If they all like it, it gets emitted by the handler. When given a message, oh, I just said that. The logger calls its filters, and if they say yes, calls the handlers. This, therefore, is a call graph. Made of objects, yes, but that each act like a verb. It's not a call graph made lexically by def in a function and literally writing, call one filter, call another filter, and then call the handler to emit. It's a dynamic call graph built in runtime out of live objects. Seeing this class might have given some of you very distant memories. Back in 2012, Jack Dieterich gave what must be the most popular Python talk ever, at least by view count on YouTube. He gave his famous talk, Stop Writing Classes. You might have been thinking of him when you saw me write this class, because this is exactly the kind of class he tells his audience to beware of. What is his verdict? He says, when he puts something similar on his screen, this is not a class. It has two methods, one of which is init, and the other method is named call. This is not a class. And so, because he saw lots of situations where people were needlessly writing classes, It's a thing in the early 20-teens. Because he saw situations where there were just needless classes, he was teaching people to back down, recognize that maybe this is just a function, and rewrite it. But what if we need to do two-phase configuration like this, where we provide the pattern up front and then it gets used later? He recommended we could rewrite as a partial. Go look at his talk if you want to see that maneuver. Those of you who know functional programming know that Python would also let you do this as a closure, where the pattern is passed in and then the inner function receives the message. I won't do that on the slide. Go look up closures if you're interested in that mechanism. I instead want to nuance a little bit what Jack said. He said this is not a class. I think you'll see that in the terms I'm defining in this talk, what we would say instead is, this is not a noun. This isn't a data structure that stores messages. This is a verb. It's an action that fires over and over, but without maintaining any state, and so it is not a noun. Here's something Jack didn't mention when he said stop writing classes. Class instances can do things that closures and partials can't, or at least can't do easily. In particular, introspection. Because the logging module has filters and handlers that are plain old classes with plain old instance variables, plain old object attributes, you can just ask a filter for its dot pattern. You can just ask a handler for its file name. You could ask a logger for its dot filters and dot handlers and inspect those lists. They're public attributes. That powered what maybe was my favorite project of all time to do. It's a single page or two of Python code. I published it as logging tree in the Python package index. You call logging tree.printout, and I go into the logging module with whatever your database code and web framework code and all of your other code have filled it full of loggers. And I walk the tree and I print them all out. And this has helped hundreds of people over the years debug some very frightful logging situations. And I was able to do it. I was able to go in and just see how the loggers were set up, because they're public objects with plain old instance attributes that I could inspect. Introspection is one of the real powerful things that's available if you do write a verb, as we saw from a class. All right, so if encapsulation doesn't just mean writing a class, since I can also write verbs with classes, then when do you start your journey into encapsulation, into the crafting of nouns, into adding behavior to data? Encapsulation starts when what might have been a simple data structure, a little data class that just gives you some names by which to refer to three pieces of data, gains a behavior. That's when you're starting encapsulation, when you think, you know, this little feature I need to add, I think it really belongs over with the noun. I don't think it belongs over with my verbs. You're beginning your steps into encapsulation when you get a Django model and add the first method of your own. It has lots of other methods and capabilities that someone else wrote, but you're beginning your journey into encapsulation when you decide to add a method to that data. That is what puts you over on the right side of this diagram, where you're now beginning to put action, to put code, to put procedures over with your data store. When you embark upon encapsulation, you become responsible now for the design of a noun. Well, I've already described a verb. What is a Pythonic noun like? From looking at my own code, looking at the libraries I really respect, this is what I think is at its core. Verbs, again, are stateless, idempotent functions. Nouns are stateful, mutable data Stateful because they remember things. Lists and dictionaries remember the items you give them. Mutable because very often data structures can be changed. Everything from a Python list up to a pandas data frame lets you overwrite items and change its content. Nouns are stateful. They remember and have a memory. Mutable data. And therefore, in Python, I find that the well-designed ones have these two attributes, which I will call legible and shallow. Legible, I mean they shouldn't have hidden state. Legible, you should be able to print or inspect a noun from code and see everything inside of it, to see everything that it's storing, and thus to be able to predict the outcome of every method and operation that it supports. Now, that doesn't mean that you see how it stores the information. It's fine for a noun to hide its implementation. A Python dictionary keeps several tables in memory and doesn't tell you anything about them. But the dict doesn't hide its state. If you print out a Python dict, you see every key and every value with nothing hidden. You don't get told about the implementation. How is it remembering all those keys and values? How is it remembering their order? You're not told. It's hiding its implementation, but it isn't hiding its state. If you print it, you see everything about it. What do I mean by shallow? I mean that each method on a noun should perform a single operation and then return control back. It shouldn't start an uncontrollable cascade of actions on other nouns, on other data structures. When you do something to a list, when you add something to a dictionary, Python accomplishes that and returns control. When you do something to a data frame, it returns control. Shallow. In your call graph, the operations on nouns should be leaves of the graph, should be the little dead ends at the bottom where something happens and completes and returns control. Now, why do we tend to design our data structures that way, to be legible and shallow? I'll offer a motivation. 2 reasons. When debugging, we're dealing with both our code, verbs, and nouns, our data structures. And there's an argument from very early in the history of computing that the nouns are supposed to be the easy part. The data is supposed to be the simple thing that you can reason about as you're wondering what all your subroutines are doing. Back in '75, Fred Brooks, this is paraphrased, said to his developers, "Show me your code and I'll probably be mystified. But draw a picture of your data structures and I won't usually need your code. It'll be obvious." He had learned that the data is supposed to be what's easy to look at, and that the code, you'll usually understand better what it's doing if you have a clear picture of the data, and you can only do that with simple, legible data structures. The other reason is when you're staring at a PY file, where is the code? It's right in front of you, in the .py file. Well, then where is the data? It's not on the page. It's in your imagination. As you read through code, you are just reading off the steps that the code will perform, but you're having to keep in your head the list, the dictionary, the data frame, and step it forward from one state to the next. As you read my little segments routine as I wrote it, you could see something like tprev equals t sub 0 in that first line, but you had to picture in your head what that was doing to the time array. The data has to live in your head. You have to model it in your head with chemistry. The data, therefore, needs to be simple because nouns need to be simple because they are the invisible half of reading code and reasoning about code. Nouns, in the patterns I see working best in the most famous Python libraries, stateful mutable data usually has the properties of being legible and being shallow. With all of that background, I can now tell you what object orientation was in its most academic and pernicious form, which is what I have time to cover here. Object orientation was a ban on standalone verbs. It wasn't a concept. It wasn't a part of your system. Under object orientation, the left side of this diagram, which is where I believe most code belongs, disappears. Object orientation recommended that you attach every line of code to the nearest noun that it touches. This resulted in constructions where a routine that needs to touch something on object K and then object L, and oh, nope, then we need that other datum from object K, winds up being a cascade of methods back and forth that are mutually calling one another between the two classes in order to get a maybe pretty simple operation accomplished. The result was a game that I like to call method ping pong. In order to understand what a part of the code was doing, you had to constantly switch back and forth between the methods on multiple objects that were each invoking the other. Oh, and then there was all kinds of fun when you said, oh, well, routine C doesn't do exactly what I would like. I need to adjust it. Oh, they said, when it needs to be adjusted, you just need to write a subclass of K where you define your own version C. So now you get to play method ping pong where you're not only bouncing back and forth between class K and class L, but you have to remember that whenever there's a call to C, it's not going to be K's C, it's going to be your subclass's C, so you need to go to a whole different file. You wind up with Python objects or Java or C++ objects that you can't understand by reading a single file, because the behavior of the actual object constructed at runtime is scattered across all the files of your application. To their credit, the Gang of Four, with their big blue book, they knew that inheritance was usually an anti-pattern. Favor composition over inheritance was the big motto that they had in their introduction. There's on my Python patterns site, there's an article called Composition Over Inheritance, if you'd like to dig in to what they meant. Many Gang of Four design patterns were just designed to escape from object orientation, to help teams that had made the mistake of object orientation redesign their code to fix that. But that's why so many design patterns went away. They could disappear, along with the bad practices they were designed to correct. We didn't need the remedies anymore once the bad design wasn't being enacted anymore. So that was what object orientation was, and it's not generally how we build objects in Python. In Python, once you get enough practice with encapsulation, you might attempt its greatest feat, the creation of the API. An API hides a whole system of verbs and nouns behind an object that wraps them up as a new noun. It makes a whole subsystem look like a new stateful data store. Perfect example is the pandas data frame. It actually stores its data in more primitive data structures, NumPy arrays, lists, dictionaries, and some other more specialized indexes and things like that. It has subroutines you never see or need to read that helps it manipulate those lower level data structures. And then it wraps it all up for you inside of what is, from your point of view, a noun. What, from your point of view, is a, if not simple data structure, at least a legible one. You can print it out and see all the rows and columns and all the data. If you print the data frame and call .info on it, you should know everything about it and be able to predict the outcome of any of its methods that you could call. A pandas data frame, thus, in my terminology, is a noun. It is stateful mutable data, but that its designer made sure is legible. You can print it, inspect it, and see everything about its state. And shallow. Each of those methods, I mean, some of them do very fancy statistics or return a new data structure that's been pivoted. They might do big things, but they each get their thing done and return. They don't go fire off methods on other objects. They do a job on this piece of data and they return. Legible and shallow. Now, a real-world API is, just to complicate this diagram a little, it's rarely a single object. Usually, it's several that cooperate. So I was actually making a data frame sound too simple. In fact, you start a conversation with it, you'll soon find yourself talking to an index object or a series object when you want to start talking to the columns. Just like requests. Oh, you're talking to one object. I created a session. But for each request you do, you get back a different response object. So in fact, a real-world API is usually a little constellation of objects that are helping encapsulate and hide some details from you. But the several objects still cooperate to maintain common state that, if it's well designed, is legible and shallow. To review, you start out using nouns and verbs. Maybe you then try to invent new verbs. If you're quite a bit along, you might even try to invent new nouns as you progress from novice to expert. My claim is that by supporting this range of approaches to writing code, Python helps you learn. Your first procedural code might all be in main, but you're getting practice using nouns and verbs written by the experts. That experience with using abstractions that other people have written might help you design functions of your own. If someday you write your own API, you'll use your experience with how other libraries have done encapsulation. In conclusion, by letting you use nouns and verbs before you have to build them yourself, Python lets you walk before you run, before you fly. Thank you very much.
Thank you very much. So I feel inspired and informed. How many of you feel inspired too? Can you raise your hand? Okay, let's call it 100%, okay? Let's keep it for a photo, okay? Brandon,
Oh, for a photo. 1, 2, 3. Thank you.
Thank you. So we still have some time for, I don't know, 3 questions, and after that we have a reception for a drink, so on. So if you have something very important to ask that everybody needs to hear,
and I will happily answer quieter questions all night if you want to ask individually.
Yeah. So do we have any big questions right here, right now? I see 2 hands there. Yes? Oh.
The first example you gave us with temperature and humidity, you said that was an actual project that you did, right?
Yes.
And the problem was that you wanted to iterate over a few thousand data points just to draw yourself a graph. And then after you built your initial piece of code, you decided that that didn't look great, so you'd go and optimize it. My question is why?
Because, for me, that's what makes programming fun, is to really, really get to that point where, oh, this code looks, it's just, even just looking at it right now on the slides, when it hits that slide where I'm just using slicing and the only work I have to do is to find the indices, I'm happy. And applause. But you're bringing up a very important topic. Where do you stop? Because you can spend a lot of time just making a little piece of code better and better in a way that is counterproductive to a larger project. I don't have time at the moment to get into some of the bigger ideas that have been in some of my other talks, but I'll say that generally you should write everything twice. And there's other speakers and other writers that have said that in computer science. It's rare that your first try is going to be that brilliant, perfect one. General and actually, mathematics instructors say that one problem with, say, proofs class is that students are so desperate to just get out of it that they will hand in the first proof that they come up with for a particular problem, but it's writing the second and third proof for that problem that lets you see, oh, there's a much easier way through to this solution than the first one I happen to think of. And writing code, like solving lots of other problems, it's just rare that our first idea is the best one. So even when you're under a deadline, even when you're working towards something, it's generally a good idea to try something out 2 different ways, and to sometimes try rewriting something in order to test out a different approach. Because in general, a year from now, your code base will be in such better shape if you do that, that it will win you back more than the time you spent in quickly doing 2 little tries. And I remember, I'll just finish my saying, when I was a new programmer, I would write things 2 or 3 different ways. It often wasn't, when I was a novice, I didn't know whether to use a list or a dictionary for a certain problem. I didn't know why it was so slow one way and faster another. And it was really important for my learning to try things 2 or 3 different ways. Sometimes find a better way. Sometimes I'm like, oh, nope, first wave is best. Back up to that first wave. Didn't need to use list there. I would even in production code, it's often helpful to do it twice. Good question. Excellent question.
Thank you. I have such a baby question. So when we start creating our own user-defined functions, so are they verbs or nouns?
If they don't remember things, if they don't keep state, if they don't accumulate information secretly somewhere, then they are verbs. Saying def and writing a function, as long as it's not secretly storing information on a global, is a verb. Thank you.
Last question, anyone? Okay. Oh, right there, sorry.
Right over there.
So in your stages, you use procedural, abstraction, and encapsulation. And when I saw that, I was tempted to associate abstraction with functional and encapsulation with object-oriented. Towards the end, I totally understood why you didn't want to use object-oriented for encapsulation, because you were making a strong point about what object-oriented in a sense was and should not be. But could you... Yeah.
So what you might be... There is, so this might get in the direction you're going, there is a style of programming called functional programming, and there's several computer languages dedicated to it, where you only ever do abstraction. There's not a concept of attaching methods to a class. Instead, everything is a stateless idempotent function by definition, and any data is an immutable data structure being passed around as an argument to or a return value from those functions. And so all of the issues with maintaining state never even arise. So it is possible to be very extreme with everything will be a verb and or an argument passed to one of my functions, and there will be nothing else. It is my observation that that is not how the Python community yet has decided to craft code. We do in our code seem to have a place for state and statefulness. When we want to do a requests, make a web request with requests, we just do it and we don't start talking about monads, right? We just do it. Hey, it's an action in the world. I just went and made a request. And of course, your functional programming grad student friend is like, no, man, you didn't just make a request. And you're like, I just printed to the screen. And your grad student functional programmer friend is like, no, that's impossible, man. And you're like, well, why is it impossible? Your friend is like, if you just think about it hard enough, it's impossible. It's monads, man. It's monads. And so like if you think enough about the definition mathematically of a function, mathematically of data, you can get yourself into this state where it's just completely normal that every function is immutable and data can't be changed. And printing to the screen or making a web request become these weird exceptions that you can hardly think about. The reason I structured the talk not going in that direction, but going ahead and on the right side of the diagram, giving a place for that pandas data frame that just changes state, as you call it, and add and remove columns, is because that's the state of the art in Python today. And we seem to have managed it in quite a few big projects so far, but I believe by those two habits of making nouns very carefully legible and shallow. But the functional programmers have gotten into so much trouble with so many stateful nouns in so many earlier decades, they have interesting ways to dismiss that right side and have all data structures be passed in and out and not persistent. Does that address where you were going? We don't know. Thank you for the question.
So thank you. If we missed your question, sorry for that. We can continue afterwards at the reception where you can share some tricks and chat once more before you left. And thank you, Brandon, once more. Okay.